Hey folks, Ms. Gosling here. In this video, you're going to learn about subatomic particles. By the end of the video, you'll be able to explain the important elements in the standard model of particle physics. So let's go ahead and get started. So in your chemistry class, and in this class so far, we've talked about protons, neutrons, and electrons as the three key subatomic particles. Thing is, while we can't break down electrons into smaller pieces, both protons and neutrons can be broken down into smaller pieces, which we call quarks. So in this video, what we're going to be focusing on is those tiny particles of matter that we can no longer break into further pieces. We call these quanta, and this is where the term quantum mechanics comes from. And they're called quanta because something that is quantized when it can be broken down into discrete elements, versus something that is quantizable, we could break it down into chunks like so, versus something like a function, which is continuous. So everything in our universe can be broken down into discrete chunks of matter, and we're going to be learning about the names of some of those kinds of matter. So let's start by talking a little bit about the history of the particle explosion. So in 1928, the British physicist Paul Dirac predicted that an antiparticle of the electron, which we call the positron, and you can see it's pictured here, he predicted that it would exist, and that when our positron and electron crash into one another, they will go through something that we call annihilation and turn instead into photons, so creating pure energy. So, for example, when our positron and our electron hit each other, those two photons that are created are going to have the exact same energy as the mass of the positron and electron. So their masses are going to be getting converted into energy. We can actually have the exact opposite happen as well. So a photon can interact with a nucleus, and that can produce a particle and antiparticle. So that energy can get converted back into mass. So we call mass turning into energy annihilation. When energy turns into mass, we call that pair production. Now, what's really important to know about our particles and antiparticles is that our particle, in this case, we have the electron, has a given mass, it has a given charge, spin, baryon number, lepton number, and strangeness. Although we don't really have to worry about strangeness for any particle except for the strange particle and its antiparticle. But anyway, what will happen is that the antiparticle of that particle is going to have the same mass, but is going to have the exact opposite charge, spin, and other key subatomic key particle qualities. So I think the thing that is most important is that our charges are opposite. But again, mass is the same. I'm going to go ahead and just really quickly list out everything else that is opposite. So charges are opposite, as are, again, spin, baryon number, lepton number, and strangeness. So again, we're not going to worry too much about spin in this class. For baryons, we'll worry about baryon number. For leptons, we'll worry about lepton number. And in the future, we will worry about what baryons and leptons are. And we only need to worry about strangeness for the strange particle, the strange quark, and the anti-strange quark. So we're not going to worry about that in a situation such as our electron-positron pair. So Paul Dirac predicted this, and we actually were able to figure out that this pair production, this particle explosion that was predicted by Dirac, is actually supported by some experimental data as well. And from all of our research into particle physics, we discovered this. We were able to develop what we call the standard model. Now, the standard model is set out in a very similar way to the periodic table. So what we're looking at three generations of matter. Our first generation is the lightest, and as we move across, our mass is going to increase, while other key elements of our standard model are going to remain the same. Now, you'll also notice we split things up between quarks and leptons in purple and in red and green. We also have a whole series of things in red here. And we have two things that are separated out entirely. So we're going to be breaking down each of our key parts of the standard model in this video. And we're going to start with leptons because they're what you guys are probably most familiar with since we've been dealing with the electron quite a lot. So leptons are all members of the electron family, and our leptons are going to increase. Our leptons are the electron, the muon, the tauon, and all of their antiparticles. So the anti-electron, i.e. the positron, the anti-muon, and the anti-tau particle are also all considered leptons. All of our leptons are going to have a charge of -1, which means that all of our anti-leptons have a charge of +1. Now, the second line of our list of leptons is our list of neutrinos. So we have the electron neutrino, muon neutrino, and tau neutrino. And all of our neutrinos have no mass and no charge. They really exist as a way to conserve energy, or really conserve momentum in some of our subatomic particle interactions. Now, I do want to mention our leptons have a lepton number of 1. Our anti-leptons have a lepton number of -1. So what we'll see is that our mass increases across the generations. Our charge for all of our leptons is -1, and our lepton number for all of our leptons is +1. For the antiparticles, we flip that. So our charge is +1 and our lepton number is -1. For our neutrinos, so our second row, we have a charge of 0, and we have a charge of 0 for the antineutrinos as well. Our neutrinos are all going to have a lepton number of +1 because they are still leptons, and their antineutrinos will have a charge of -1. A lepton number of -1. Now, one thing I want to mention here, we represent the electron with an E. If we want to represent the anti-electron, the positron, we're going to just put a bar over the E, and that is going to represent our anti-electron. Similarly, our electron neutrino is represented by a nu, it's a Greek letter, with a little e as a subscript to represent that it's the electron neutrino versus the muon or tauon neutrino. And the anti-neutrino is going to, again, have that bar over it. So that is our little introduction to leptons. Now let's talk quarks. Now, y'all have probably heard about quarks. It's something people like to mention a lot in, for example, Marvel movies to explain magic in a way that sounds like it's scientific. Quarks, we have 6 quarks: up, down, charm, strange, top, and bottom. And one fun fact about our quarks is that our top quark and bottom quark actually have had their names changed. So if you look at older textbooks, instead of seeing top and bottom, you'll actually see truth and beauty. We changed those names to make it a little bit clearer. Another fun thing about top and bottom quark is the top quark is on top of our bottom quark in our standard model of particle physics. Now, just like with leptons, we have 6 quarks and we have 6 antiquarks. So each quark has a charge of either positive 2/3 times the charge of the electron or negative 1/3 the charge of the electron. Antiquarks have the exact opposite. So our up, charm, and top quarks have a charge of positive 2/3 times the charge of the electron, while our down, strange, and bottom quarks, so that second row, have a charge of negative 2/3 times the charge of the electron. Or, negative 1/3 times the charge of the electron. I'm going way too quickly here, guys. My apologies. Now, our antiparticles are going to, of course, have the exact opposite charge. So they'll have a charge of negative 2/3 e and positive 1/3 e for, again, our antiparticles. And just like our leptons, as we move across our generations, our mass is going to increase. So our up and down quarks are the lightest, our top and bottom quarks are the heaviest. Now, one thing that is really, really, really important to know about quarks is that quarks are always going to be confined. So you're not going to ever be able to go out in the universe and just find an up quark on its own like you would be able to find an electron hanging out on its own. Instead, they're going to exist in groups, and we call these groups hadrons. Any group of quarks is a hadron, but we can split our hadrons up into mesons and baryons. So a meson consists of a quark and an antiquark. For example, our pion, which we represent like this, is going to be made up of an up quark and an anti-down quark. So it's going to have a charge of positive 2/3 times the charge of the electron plus 1/3 times the charge of the electron, which are the charges of our up and our down quarks. Thus, its charge is going to actually just be positive 1. Another example of a meson is something we call B0. That is going to consist of a down quark and an anti-bottom quark. So our down quark is going to have a charge of negative 1/3 e, and our anti-bottom quark will have a charge of positive 1/3 e. So we're going to have a total charge here of 0. So that is kind of our first way to combine quarks, to confine them. And we call a combination of a quark and an antiquark, one of each, a meson. We can also confine our quarks into baryons, and baryons are going to be made up of 3 quarks rather than just 2. So our baryons are all going to be made up of either quarks or antiquarks. So while our mesons are a combination of quark and antiquark, our baryons contain one or the other. So the easiest example of a baryon is the simple proton, which is made up of 2 up quarks and a down quark. So that's going to give it a charge of plus 2/3, again times the charge of the electron, minus 1/3, or a total charge of positive 1. Similarly, the neutron is another great example of a baryon. A neutron is made up of 1 up quark and 2 down quarks. So it's going to be plus 2/3 e, minus 1/3 e, minus 1/3 e, giving it that total charge of 0, which we know is the charge of the neutron. Something a little more exciting, the antiproton, which is made up of 2 anti-up particles, or anti-up quarks, and 1 anti-down quark. And that is going to give us, of course, negative 2/3 e minus 2/3 e plus 1/3 times the charge of the electron, for a total charge of negative 1 times, again, the charge of the electron. And finally, moving to some exciting Greek symbols, we have our lambda baryon. And just so y'all know, you do not need to memorize these. I just want to introduce you to the wide world of different baryons that are out there. Because so far, we've only made baryons out of up and down particles, up and down quarks. I'd like to try to show you one that's made up of not up and down quarks. So our lambda baryon is made up of an up quark, a down quark, and a strange quark. So it's going to have that same charge as a neutron in the end, right? Because we have positive 2/3 e from our up quark. We have negative 1/3 e from our down quark. And we have negative 1/3 e from our strange quark, giving us a total charge still of 0. Now, the key thing here, guys, is to remember first mesons, quark, antiquark, baryons, 3 quarks or 3 antiquarks, are both considered hadrons, and they're both examples of quark confinement, i.e. quarks being found only in groups, not on their own. The other key thing that I want to point out to you is that our mesons and our baryons are going to have charges of either +1, 0, or -1. So quarks all have fractional charges, but our mesons and baryons will all have whole number charges. And again, that's +1, -1, or 0. So just a note, you're not going to be making a bunch of baryons out of just kind of random combinations of quarks. We're going to be making them up out of combinations of quarks and antiquarks that create +1, -1, or 0 charge. Okay guys, so we've almost made it through the video. I do want to explain the next set of particles, totally different from anything you've seen before. So this is our list of orangey red particles that we saw on the right side of the periodic table of particle physics, or the Standard Model, as is more commonly known. And we call these our Gage bosons. So we've got the gluon, the photon, the Z boson, and the W boson. Now, these 4 bosons are also known as exchange particles, and each one of them is used to moderate a force. So these 4 particles are all associated with different forces. So the gluon is associated with the strong force. And what it does is it mediates the strong interaction between different particles. So this is the particle that helps hold our nucleus together. So the gluon is going to act only on quarks, gluons, and hadrons, so things that are close together. Because what's really important about the strong force is it's very strong, but it also only works over very short distances. So the gluon is going to mediate the strong force. Next we have the photon, which you guys are very familiar with, and that is going to mediate the electromagnetic forces. So both electricity and magnetism are mediated by photons. So as you know, our photon is only going to do anything if our particles are electrically charged. So our neutrons are not going to interact with our photons as exchange particles, but our protons and our electrons will. Finally, we have the Z and W boson, which both help mediate the weak nuclear force. So we represent these by either W positive, W negative, or Z, which is neutral. And when we have weak nuclear interactions happening, which we'll get into a little more what that means on my next video. When we have those weak nuclear interactions, it's important to know the Z and W boson are the Gage bosons that make those occur. Now, one thing I also want to mention, well, 2 things really. So first of all, I do want to mention that the strong nuclear force is carried by gluons, but also by mesons, which are, just to remind you, are quark-antiquark pairs. So mesons do this as well. This is very messily written, but that's okay. The other thing I want to mention is you may have noticed that there is a glaring missing force here that we have spent a lot of time talking about. So you might ask, what is the exchange particle for gravity? Well, we have a theoretical particle that would work as an exchange force for gravity called the graviton, but as of now, it's remained undiscovered. So right now, gravity is kind of the one force that really doesn't fit very nicely into the Standard Model. You may remember I mentioned in class that that the Standard Model, that quantum mechanics and general relativity are mutually exclusive. They don't both work together. This is one reason why. So again, the Gage bosons are a mechanism for fundamental force interactions, and you'll notice that the larger the mass of the exchange particle, the lower the range of the force. This is because our Gage bosons exist as what we call virtual particles. So our Gage bosons really only exist during the interaction. So they need to, and the interaction needs to happen before the particle is detected. So if the particle is heavier, it's not going to be able to last as long in the air without being detected. Think about, for example, throwing, how much easier it is to notice a bowling ball flying at you than a golf ball flying at you. So again, because these are virtual particles, the lighter the particle, the farther the distance that the interaction can occur. So finally, we come to the last piece of our standard model, and that is the Higgs boson. So the Higgs particle is really, really important because the Higgs particle stands a little bit on its own from the other particles, and it explains why some of our particles have mass. So the Higgs particle is kind of like our Gage bosons, in that it mediates something. It's a virtual particle. And because it has a really large mass, it takes a lot of energy to produce it, and it's not going to exist for very long. And what it does is it allows us to explain why our leptons and why our quarks and our bosons all have mass. Because initially we didn't really have, our initial theories predicted that the leptons and quarks should have zero mass, which we know they don't. And the Higgs boson and that interaction with the Higgs field is what we can use to explain why all of these particles have mass. For a long time, the Higgs boson was actually completely theoretical. It was actually discovered well within all of your lifetimes in July of 2012 at both CERN, which is the Large Hadron Collider in Switzerland, and at Fermilab, which is a big particle physics lab in the United States. So, takeaways. First of all, particles can be categorized as quarks, leptons, exchange particles, except, of course, for the Higgs boson, which is something unto itself. Every particle has an antiparticle, which has an equal mass and opposite charge, and every type of particle is responsible for a different part of our observed universe. So all of these particles come together to create the things that we are able to experience and to see and to observe. So with that, this has been your introduction to the standard model. I know it's been a lot of new information, a lot of new vocabulary. If you are feeling a little overwhelmed and a little confused, I'm going to recommend taking a look at chapter 7.3 in the textbook. It goes into a little more depth into some of this, and you may find it helpful for building your own understanding of this topic. With that, I'm going to go ahead and let you go. In the next video, I'm going to be talking about how we use all of this information to solve problems and to better understand particle interactions.